Hello and welcome. My name's Cameron Sinise and I lead the AWS Container Services business in Australia and New Zealand. Today, I'm going to be talking about containers and Kubernetes and about building and running your first Kubernetes workload with Amazon's Managed Kubernetes Service, EKS. This is a Level 200 session designed for developers and operators with experience in concepts like infrastructure as code and software development. First, I'm going to talk a little about what containers are and why you would consider using them. Then I'll be talking about why Kubernetes is a great way to orchestrate containers and how EKS makes that a really great experience. And then there'll be a demo, and in the demo, I'll walk you through building and shipping a Java application in a container image, launching an EKS cluster, all automated as code, and then finally have Kubernetes run our containerized application on EKS. The only real constant is change. And what I mean by that is organizations want to be more agile so they can innovate and respond to change faster. More than ever, organizations want to move with speed and focus on innovation and delivering systems to production more efficiently and more safely. But in reality, teams are spending more time than they really can afford to on manual operations. This desire to deliver more and faster and with better quality has become the driver for a lot of transformation. What do our most successful customers want from us? What lets them innovate quickly, compete in a global market, and deliver value for their customers? They want their teams to focus on delivering applications as rapidly as possible. They want their infrastructure to be reliable, highly available, secure, and cost-efficient, and customized to their needs. They want a proven track record of scaling to whatever size they need and to scale up and down rapidly. And they also want security and isolation and control over the access permissions, and they want automation to reduce human error. Because of all of these requirements, we've seen a large push towards containers. The decision to adopt containers brings a raft of advantages. Containers allow for a more clear separation of concerns. Developers can now own both the application and its dependencies, and operators can focus just on the deployment and management side of the equation. Containers are very lightweight as compared to virtual machines. They start much faster and they use a fraction of the memory compared to booting an entire operating system. Containers provide a high degree of portability and allow for consistency across a range of deployment scenarios, such as different host operating systems, including Linux, Windows, and Mac OS, on virtual machines or bare metal computers, on a developer's local machine, or in on-premises data centers, and of course in the public cloud. And finally, containers work well for building systems that use a service-based architecture, such as modular microservices. And for all of these reasons, we're seeing containers becoming the new standard unit of management for compute workloads. Before we jump right in here, as a matter of housekeeping, there are a couple of concepts and components in the container space that are frequently rolled into the single term container, but are actually distinct and separate elements. Terms like containers and images are used interchangeably, but there are some important conceptual differences. Generally speaking, we're dealing with four main components when reasoning about building and running containers. First, we have the container image, which is a lightweight, standalone, executable package of software that includes everything needed to run an application. The application code, system tools, system libraries and dependencies, and associated settings. The accompanying illustration depicts the elements of a container image. The container engine is a software application that accepts user requests, including command line options, retrieves container images, and from the end user's perspective, actually runs the container. A container is the runtime instantiation of the container image, and the container host is the system that runs the containerized processes. Okay, so you're interested in getting started with containers, but you're probably wondering, how do you build and deploy containers to a production server? What's the process? And how do people do this in the real world? Generally, when creating software that will be deployed in containers, changes will go through four main stages. So first, a developer will write the code. Then we build a container image. The container image is pushed to the server, either directly or via an image registry. And finally, the image is launched through the container runtime, and the application is running on the container host. Of course, this is a very high-level view of the stages involved. At a lower level, you might use a bunch of different tools or methods, but broadly speaking, the overall process is going to be the same. And this is the flow that we'll walk through later in the demo. In stage 4 of our demonstration, it will be Kubernetes that will run our container on EKS. Turning our attention to Kubernetes, let's start by answering the question, what exactly is Kubernetes? By strict definition, Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. We've established that containers are a good way to bundle and run your applications. In a production environment, you need to manage the containers that run the applications and ensure that there's no downtime. For example, if a container goes down, another container needs to start. So wouldn't it be easier if this behavior was handled by a system? And that's where Kubernetes fits in. Kubernetes provides you with a framework to run distributed systems resiliently. It takes care of scaling, healing, and failover for your application, provides deployment patterns, and a lot more. Some of the great functionality that Kubernetes can provide you with includes service discovery and load balancing, storage orchestration, automated rollouts and rollbacks, automated bin packing, self-healing, and secret and configuration management. Given the choice, a lot of organizations choose to run Kubernetes on AWS, and actually 80% of all containerized applications in the cloud run on AWS. While a majority of our customers choose an AWS managed service, we also recognize that customers have specific needs to self-manage Kubernetes on AWS. We're committed to providing the best experience regardless of how customers choose to run Kubernetes. Teams choose Kubernetes for its vibrant ecosystem and community, consistent open source APIs, and broad flexibility. Customers rely on Amazon EKS to handle the undifferentiated heavy lifting of security and operating Kubernetes at scale. Amazon EKS provides the flexibility of Kubernetes with the security and resiliency of being an AWS managed service. As customers move a larger portion of their workloads to Kubernetes, Amazon is meeting our customers' demands with Amazon EKS. Here are a few key attributes that our customers have come to appreciate about EKS. Firstly, we do not modify open source Kubernetes. EKS is fully upstream and certified conformant Kubernetes. We even backport security fixes to ensure we're consistent with open source. For example, we made kubeproxy enhancements to prevent bad actors from getting access to your cluster, and these enhancements are now part of upstream. We support upstream Kubernetes versions for a longer time period. We support up to 4 versions of Kubernetes, which gives our customers sufficient time to roll out upgrades. As part of this, we even backport patches and fixes and upgrades to Kubernetes versions, even the ones that the community may not currently support. We provide a managed Kubernetes experience where we do a lot of work to select the right Kubernetes version, validate dependencies to provide the security, stability, and operational excellence that our customers rely on us to deliver. Our customers choose EKS because it allows them to focus on their business applications and offload the undifferentiated heavy lifting, the tactical operations associated with self-managing infrastructure for application deployments that add no business value. Amazon EKS makes it easy to run Kubernetes without having to validate, build, and operate Kubernetes on your own. EKS provisions and scales the Kubernetes control plane, including the API servers and back-end persistence layer, all across multiple AWS availability zones for high availability and fault tolerance. It automatically detects and replaces unhealthy control plane nodes and provides patching for the control plane. Amazon EKS performs managed in-place cluster upgrades for Kubernetes, greatly simplifying cluster operations and allowing you to take latest Kubernetes features as well as updates to Amazon EKS configuration and security patches. The AWS Cloud Development Kit, the AWS CDK, is an open source software development framework to model and provision your cloud application resources using familiar programming languages. You can do this in different programming languages such as Python, JavaScript, TypeScript, Java, or C#. With CDK, you'll be much faster than with previous tools because you work with your familiar language and concepts, classes, and methods. And with the CDK, we provide many sane default values. So there's no need to read a lot of documentation. You can just get started quickly and safely. There are three main components of CDK: the core framework, the AWS construct library, and the command line interface. With the core framework, you can create and structure apps that contain one or multiple stacks. Stacks are logical units of infrastructure which contain multiple resources and are actually mapped one-to-one with CloudFormation stacks. The AWS construct library is a set of components crafted by AWS to create resources for specific service. This helps to decouple libraries and use only the dependencies that you need in your project. And the CDK CLI helps to interact with the core framework to initialize project structures, inspect differences between deployments, and deploy easily to AWS. In our demo, we're going to be using the CDK to provision our EKS Kubernetes cluster, and a typical CDK development workflow will follow these 5 main steps. We start our project by executing CDK init, which will generate a project structure for our specific programming language, so we can then start creating our apps, add stacks, constructs, and resources. Once we're done, we need to build the project. For example, if using TypeScript, we'd submit the command npm run build. Next, we need to synthesize our code to a CloudFormation template. For this, we submit the command cdk synth. This will generate the CloudFormation templates and assets, and we call this bundle the Cloud Assembly. Before we deploy, we can inspect the impact of deploying this Cloud Assembly. This will tell us which resources will be deleted, updated, or created. And with the command cdk deploy, we push the changes to the AWS CloudFormation service, and from there the service will create cloud resources in our AWS account. In the following section of the presentation, there will be a demo where I walk you through the end-to-end process of building and running your first Kubernetes workload with Amazon EKS. There are going to be 5 main steps, taking us from building our container image to running it in the cloud. To help you get a picture of the solution architecture before we begin, let's walk through the stages of the exercise with an accompanying diagram. In step 1, we build our app locally and create the container image in a multi-stage Docker build. In step 2, we push our container image to the Elastic Container Registry. Kubernetes and the container runtime will pull this image to the container host at stage 4 of the process. In step 3, we use the CDK-based Quick Start template to deploy our new EKS environment. In step 4, we set up a Kubernetes deployment and ingress for our Java application. In step 5, the AWS Load Balancer controller and external DNS set up an application load balancer and Route 53 configuration to action our ingress and make our application accessible from the internet. This is section 1 of our demo, and we're going to start by containerizing our application. As you'll see, it's a fairly simple Java application based on the Spring Boot framework that will just print out "Hello World." Being a Java app though, we'll need to compile it first in order to actually run it. Rather than needing to first install the right tooling to build our jar, such as a particular version of the Java development kit plus Maven to build it locally on our laptop, we can actually do that within a stage of a multi-stage Docker build. The advantage of that is that you'll always get a fresh build environment with all the tools you need at the right versions for every build, regardless of where you run it. This means no more spending ages setting up a new developer's laptop so they can build the app. Our continuous integration pipelines can use the same Docker file with the same base images to ensure consistency with what developers are seeing. So no more dreaded, but it worked on my machine. The issue with performing builds within your Docker environment used to be that it bloated your runtime image with tooling and artifacts that were unnecessary at runtime. Now, with multi-stage builds, we can spin up a fresh base image and just put our compiled artifacts right into there, which will become our runtime image as shown here in this Docker file. Now let's do the build. And we can see the numerous steps of the build as output from Docker as it progresses in the terminal. That was pretty fast. It only took about 17 seconds. The reason was, as you can see, many of these steps say that they were cached. Docker is smart enough to cache steps and layers so that as you iterate through your development process, it stays nice and snappy. So now that we have our container built, let's test it. We'll do a Docker run and instruct Docker to map port 8080 to our local host. It looks like our container started and our app is now up and running. If we head to localhost on port 8080, where we've exposed it, accessing that in our browser, we're able to see our application return hello world as expected. And now that we have our container image built locally, the next step is to get it running in the cloud, is to push it up to the Elastic Container Registry. Now we're beginning section 2 of the demo, where we push our image to ECR. First, we need to go to the AWS console for the Elastic Container Registry service and create a new repo. We'll call this Spring. Here's our new empty repository, and if we click the View Push Commands button, it will provide us with the commands to copy and paste, which will push our image. The most important of these commands is the one which logs into the ECR repo, and we'll go ahead and enter the command into our terminal. Great, so that login was successful. We've already completed our build, so now we want to go ahead and tag our image. So let's now copy and paste the command into the terminal. And then following that, we can perform our Docker push. And as per the output in the console, the various layers of the image are being pushed to ECR. And there we go, that was successfully pushed. And here's our image now visible in the console also. So now we're ready for running the next step, and that's running our container in the cloud. But before we can do that, we need to set up a Kubernetes environment for us to run it in. Okay, we're at section 3 of our demo, where we deploy EKS using the CDK. We've been working on a new quick start template to spin up not just an Elastic Kubernetes service, but also all of the associated add-ons, such as the AWS Load Balancer controller to integrate the ALB with the Kubernetes ingress, external DNS to reconcile Route 53 with our changes, to send our logs to Elasticsearch, our metrics to Prometheus, and so on. The EKS CDK Quick Start will provision a complete environment instead of just an empty Kubernetes cluster. The EKS CDK Quick Start is available at the AWS Quick Start's GitHub repo and also provides a detailed end-to-end work instruction to quickly and easily get your cluster up and running. The Quick Start CDK template that we're working with is written in Python. And note that we've taken the parameters that people will often want to change, and we've included them at the top of the file. So you don't need to know Python or the CDK, or go digging through the body of the template to make common tweaks or changes. A few interesting things to note about this template. As you can see here, CDK takes care of our IAM role to service account or IRSA mappings. As many of these add-ons are to configure AWS resources, having granular permissioning around their access to these resources is important. And the CDK makes it really easy and straightforward. You create the role and define the policies, and this is mapped right into a service account that can be assigned to your Helm charts. CDK extends CloudFormation to be able to deploy Kubernetes Helm charts and manifests to your cluster. So it makes bootstrapping both sides, the AWS and the Kubernetes API side, the environment quite cohesive. The last point to mention here is that the CDK has dynamic references. And a good example of where these references are powerful is by taking a look at our logging solution. So in this case, we have CDK creating a managed Elasticsearch. For this, we need the ARN of the Elasticsearch to make a policy that allows our FluentBit plugin to ship logs to this Elasticsearch instance, with all of the associated granular permissioning as well. The FluentBit will also need to know the address of the Elasticsearch in order to be able to send the logs there. What's great here is that we're able to have the CDK orchestrate the passing of these parameters around between the various dependent components, and it's actually able to build a dependency graph such that it completes the operations in the correct order of precedence. This capability is quite powerful and saves the developer a lot of cycles by removing the requirement to actually understand all of the resource dependencies and authoring template files in a strictly serial fashion. It takes about 30 minutes to deploy the whole environment that's based on this template. So in the interest of time, I went ahead and deployed one a little earlier. And rather than run the CDK deploy from my laptop, I instead used code build to provision the environment. There's actually a number of advantages of using code build, and these include the following. First, the system will keep all the logs for later reference, as we can see here. This allows us to come back at a later time and refer to them to confirm exactly what happened with our build and to validate if there are any interesting errors or warnings. Code build can also be assigned a service-linked IAM role with each of the administrative rights required to build out all of the AWS resources, rights which typically aren't assigned to users. And finally, we can set up a GitOps webhook so that any changes committed to our template in a Git repo can use an automatic rerun of the CDK deploy command, which will update our environment. This means that all we need to do to update any settings is to make and commit a change, and the pipeline will take care of the rest. I haven't touched this environment since it was provisioned a little earlier on. So what you're about to see just works out of the box with this template, having completed its run. We're now at the beginning of section 4, where we deploy our app to Kubernetes. Our CDK template deployed a Bastion instance as part of the environment build-out. It isn't reachable over the public internet, but we can reach it securely and with full audit trail via Session Manager. I'll now go ahead and connect to the Bastion and start interacting with the cluster. As you can see on our Bastion host, we have the Kubernetes command line tool, kubectl, automatically configured to authenticate and to connect to our cluster. Let's go ahead and take a look at the components we have up and running. I'll go ahead and submit the command kubectl get all. Normally, an EKS cluster is provisioned with very few components installed. But as you can see, the Quick Start has provisioned most of the common Kubernetes add-ons people might want, giving us a more complete environment out of the box to begin working with. The add-ons that will be particularly relevant to us here are the AWS Load Balancer Controller and external DNS, as you'll see in a moment, and there's a number of other add-ons here that are configured and ready to go. We want to deploy our container to the cluster, and the way we go about that is with a Kubernetes deployment. So we could go over to the Kubernetes documentation and take a copy of the example YAML spec file for creating a deployment. But in this case, there's a command built into kubectl that makes this nice and easy. We enter the command kubectl create deployment, and we then specify the image parameter as the image URI of our Spring container, which we can retrieve from the ECS web UI. Once we've pasted our image URI, let's go ahead and submit our command. And there we go. Here's our container up and running in the cloud. It's in a pod on our EKS Kubernetes cluster. Next, we want to make the application available on the internet via HTTPS and have it be provisioned behind a load balancer. To do that, we'll need to create a service, which is like a layer 3 load balancer, and an ingress, which is like a layer 7 load balancer. Unfortunately, there's no kubectl command to save us from writing the YAML configuration file. I have one here that was prepared earlier, and let's go ahead and take a look at the config, which will describe the resources that we want Kubernetes to create for us. So first, we're creating a Kubernetes service, which is like a layer 3 load balancer that's going to expose the container on TCP port 8080. Then we want to integrate that with the AWS application load balancer, and we do that through a Kubernetes ingress. Via the annotations, we can specify that we want an ALB and that we want the ALB to be internet facing, that we want it to be listening via a HTTPS port, that is 443, and that we would like it to be configured as accessible via a particular DNS name. The DNS resource is actually provided by the external DNS controller and not by the load balancer controller. What the external DNS controller does is wait for the load balancer controller to set up the ALB, and then it automatically sets up a DNS alias in the DNS service Route 53, which points to the IP endpoint address of the application load balancer. The remainder of the configuration file basically stipulates that all inbound traffic that's destined for the host name spring.jasonamica.com should be routed to our container. Next, we enter our kubectl apply command to submit our YAML spec file, and we can see that Kubernetes has created both our service and our ingress. We can see our service with the get endpoints request, and if we submit a get ingress command, we see that our ingress exists and it's already got the address in line of the load balancer, which is being provisioned. We actually can go to the load balancer section of the AWS console and watch the LB being created for us. We see initially that it's in the provisioning state, and after a few seconds of waiting, will become active and ready for use. So now the load balancer's finished provisioning, we can go over to the Route 53 DNS console and validate that our DNS record has been provisioned. And as we'll see, the A record for spring.jasonamica.com has actually been created. This means that our application should be ready and accessible over the internet. Let's enter our address in the browser as spring.jasonamica.com. And sure enough, our application is up and responding. We have our TLS secured, load balanced, and containerized application successfully running on EKS in the cloud. And that concludes our demo. If you want to get started with your first EKS cluster on AWS, then follow the link on screen to the EKS CDK Quick Start over at the AWS GitHub organization. This is the exact same configuration that I used in the demo to build our EKS cluster, including all of the additional configuration and add-ons to get you to production faster. There's also a detailed work instruction which shows you how to provision your cluster using code build, and then access your environment using the included Bastion host. Accelerate your cloud journey by checking out the featured courses to build your cloud skills on AWS, or visit the link below to explore over 550 free digital training courses. Thanks for attending. I hope you found this session useful. Please take a few moments to complete the survey. We love to hear your feedback to help us to continue to improve these sessions in the future. We really appreciate it.